formation. But we're always tracking the energy. That's what chemistry is. It's tracking electrons and energy and explaining the world based on the principles of elements. So we're doing that, and then this is blank. Cool. But it's on. Why is it blank? Yeah, if I could stay on one train, it'd be nice. Okay. So we have a delta heat of reaction, and that's going to be all the energy that's made from going from reactants to products. But we take care of it in reverse, right? We want to know the total energy of the products minus the energy of the reactants. So that's how we find the total change in enthalpy, or the total change in heat. Right? And we always know we can go from grams to moles to moles, and back to grams in any direction, right? That's the beauty of all this stuff. Why do we pick moles? Because it lets us do whole number ratios between everything that we're looking at. So with energy, it's the same thing. So we can do energy per gram, moles per energy per grams of compound, energy per moles of compound. So delta H reaction per mole of reactant can be related to any amount of reactant product through the balanced chemical equation. That's why the coefficients tell us how many moles relate to how many moles. And we can pick any part of that reaction or equation and say how much we need to make that happen. And it's like a magic formula. It's what makes chemistry magic, is that whole number ratios are available. If I see the reactants and the balanced chemical equation, I can figure out exactly how much of one thing I need to make something else. I just had so, we have alternative medicines a lot, right now. It's huge. People are selling all kinds of snake oils and stuff and talking about, oh, synthetic this is not equal to natural that. Well, synthetic this is natural that, right? So, and then I just got because I'm in a health situation, I'm getting a lot of conflicting information. And surgeons, like if you go to a surgeon, he's going to want to do surgery, whether you need it or not. I mean, that's just the business, right? Mm-hmm. So you may need the surgery, you may not. But you go to a naturopath, and they're going to say the same thing. You need to use these products because that's their business, right? So the real problem with healthcare is what's broken is individualized treatment for individual symptoms of individual people, right? We're not a group to put in a box and then just work with. Well, chemistry allows us to look at things in a rational manner to see what fits. And so if you look at a product that's synthetically made and you say, oh, that matches this organic product, it does. And then I just was saying that to one of the people that sells me snake oil, and they said, oh, well, this PhD explains the difference between this and that. And what they said was enantiomers. And enantiomers are one hand versus the other. So you can't superimpose them. A lot of organic compounds and a lot of health compounds are enantiomers. You have a left and a right. It led to a lot of problems with thalidomide. Thalidomide was great, except for the right-handed thalidomide caused deformation in human fetuses for pregnant women, and it was a big problem. The left hand was perfect, but back then we didn't know that you could separate them. We didn't know you could separate the mirror images. And they're 50-50 combinations, or what we call a racemic mixture. So that racemic mixture, 50-50, is what this guy said the difference between synthetic compounds and naturally occurring compounds are. Our naturally occurring compound is 99.9% one-handed molecule. Well, I can do that in the lab. That's not a big deal. Now, it's expensive to do compared to just doing the racemic mixture of left hand, right hand, because its stereoselectivity is crazy, and that has nothing to do with what we're talking about. But it's the idea of what you can do with a foundation of knowledge that allows you to see beyond the veil of salesmanship. And that leads to informed citizenry, and informed citizenry can make good decisions, like going to Mason Bar on a Friday night, right, Nathan? Yeah. All right, so a balanced thermochemical equation like C3H8 plus 5O2, which is a what kind of reaction? Combustion, thank you, very good. Anytime you see oxygen, think combustion. Combustion reactions are what type of reaction? Oh, there we go, redox, right? Right, because oxygen starts as an O, right, at 0, and it goes to 2 minus. So it's oxidation reduction. You could also see that right here, we have hydrogen at 8 plus 1, so plus 8 over 3. Uh-oh, that's not going to work out. So 8/3. Anyway, so it must be more than 1. Anyway, it can tell us many things. What does it tell us? A thermochemical reaction. So that minus 2044 kilojoules for the entire reaction, right, is going to tell us that for every 1 mole of, we're going to call this propane, and we will release 2,044 kilojoules of heat, right? So in this usage, we're saying it's exothermic process, right? Because the heat is negative.
Mm-hmm.
Yeah. It also tells us that 3 moles of CO2, carbon dioxide, produced with 2044 kilojoules of heat, right, are produced. So we make 3 moles of CO2, same number. 4 moles of H2O are produced with 2,044 kilojoules of heat. 4.16 grams, so now we're going to use grams to moles and then use the ratio of the total change in enthalpy. So 4.16 grams of propane converted to a mole of propane using the molar mass of propane, 44.11 grams, changes to 2,044 kilojoules. And what happened here? This number's not right.
Why does it go from negative to positive?
You don't.
Oh, okay.
Right, something, I don't know what happened to that. I think it happened, so stop it.
There we go.
Drinking. Day drinking, okay, so. There we go. And now it's correct. Control save. A lot of times I do these slides and then
So are all of those supposed to be negative as well, though, like number 2 and 3?
Okay, so what it's saying is number 2 and 3 are not negative because of the way we set it. So it comes with 2,044 kilojoules of heat. Yeah.
So release means exothermic, produce means endothermic?
No.
No?
Neither one. It's the absolute value, 2044. So when I'm releasing 2044 kilojoules of heat, you know that's negative because it's released.
Right.
When it's produced, it's also negative because now it's on the reactant side. So if it's absorbs, then it's positive. So it's the terminology. That's an absolute value. You could say it like this too. Though. I mean, that'll work. Right?
I just didn't know if it was like a error.
I mean, if it helps you understand more clearly, that's fine. But what we need to know is that this absolute value is 2044. If it's released, right, we know it's an exothermic reaction. If it's produced, we know it's an exothermic reaction.
Okay.
If it's so if it's on the reactant side, it's going to be plus.
Oh, react, okay.
Go ahead.
I thought it was only exothermic if it was a negative, not dependent on the terminology being released or produced. So you can't have a released positive number?
No.
No.
No, okay.
No, but when I was doing this, I was thinking in terms of an amount and not the sign. So that's why it would be helpful if you had that.
Okay.
Well, that's why I put it in there, because I went a step too far. So it's now saved in there. It will never be that error again. If you want to call it an error, but there we go. So anyway, you get 192.8. Follow that on your video. 192.8 kilojoules. So we have standard states that we look at reactions with, right? It's kind of like we do with gases, which we haven't got to yet either. But the gas standard states are 1 atmosphere in pressure. Aqueous solutions, 1 molar concentration. Pure substances, elements or compounds, the most stable form at 1 atmosphere, 298 K. 298 K is 25 degrees C, right? Standard heats of reaction are carried out under standard state conditions and are denoted by using a degree sign after the enthalpy. So that 0 means standard state. That's all you need to know if you see that delta H 0. And then it'll say formation, standard heat of combustion. So what happens when you burn it? It's for 1 mole of compound reacting with O2. So we have enthalpy for combustion, and we'll differentiate all these little enthalpy terms, but basically we're always looking at the same thing. So for carbon, we have certain enthalpies. This is just a table. You can see that they vary a lot, right? So if you combust carbon, you get 393.5 kilojoules. If you combust ethanol, right, which is drinking alcohol, you get 1368.8. If you do methanol, which is just a 1 carbon chain, ethanol is a 2 carbon chain, C2H5OH, it's an alcohol. The OL designates alcohol. CH3OH is a 1 chain carbon methanol, and isooctane is an additive to like gasoline, and it gives you 5,461 kilojoules. So ethanol burns at a higher energy level, but it's harder to control because it tends to just go at once. That's why the longer chain hydrocarbons that break down gives a more controlled energy burn. But we're using batteries now. We have to use other things to power those. So here's an example. So methane is claimed to be a cleaner fuel with a lower CO2 emission. Consider the enthalpies of combustion given below for the methane and octane, gasoline, and determine the energy per mole of CO2 produced. Is methane really cleaner to burn? So you have methane, or cow farts, that one of our, never mind, I'll be political. Methane plus 3/2 O2. And now, after telling you we only do whole number ratios, I'm going to say, well, we can also do partial ratios if we want to. And that's what we do as we unveil the layers of our chemistry tree. We just add 2. So we start off with a very simple definition for people who are just going to barely touch the surface. We start expanding, and then we start showing all the exceptions to what we know. Then we fit into a nice little box, just like everything else. Nice little boxes. Put them on a table in a row. Okay. Then keep score. CH4G plus 3/2 O2 yields CO. Why is that there? All right, you with me? So we're going to burn oxygen. In presence of oxygen, we're going to burn methane, and then we're going to burn a longer chain hydrocarbon. And the first time we use 3/2 O2, so per mole of CO2 produced, we get 882 kilojoules of energy, or it's an exothermic process by 882 kilojoules of energy. We can use that for work, right? And then if we use octane, we get 8 CO2 molecules, and we release 5,000 kilojoules of energy. So we make 8 divided by 5,000. 5,000 is about 856, right? So about 600 kilojoules in some. But we found out here it's already 800, right? So we get more energy in burning 1 molecule of one compared to 1 molecule of the other. If that makes sense. You see that? So delta H of minus 5,000 kilojoules per mole for the production of 8 moles of CO2, or 634.3 kilojoules per mole of CO2 produced. So we get significantly less energy for every mole of CO2 we produce from octane. So methane is cleaner fuel. How about that?
Mm-hmm.
So we should be burning cow farts. We have to burn an awful lot of them. All right. So methane is another one of those gases that's released on the planet without man's involvement, as is oil. Oil is released at the bottom of the ocean through fissures in the crust. Radioactive materials, uranium, for example, are in the earth, releasing radioactive decay. There's background radiation. When we first started using radiation, we didn't even know that, right? Because we couldn't measure that amount. But then once we started blowing stuff up with radioactive materials, we were able to realize, oh, maybe we should get a baseline. Because, you know, it's the way we didn't have funding for that. So Hess's law. So this is a state function. Remember, a state function is I can walk straight up to Maria, or I can walk all over the place, and it's still the same distance to get to Maria, even though I used a different path. I've only really traversed in a straight line, and the energy that we use in a reaction doesn't matter the steps that we use to get there. It's all going to come out to be the same difference. You start with one energy, we're going to end with another, and the path is independent. So for Hess's law, we take advantage of that to say the steps equal the total change. So that whatever path we take, we can add those steps together to get to the final thing. So which means if we only know parts of a certain reaction, we can figure it out to get to that reaction that we don't know. So the change in the enthalpy of the reaction is proportional to the amounts reacted. Well, that makes sense, right? The amount of energy changes based on how much we have. If we have a whole bunch, we're going to get a big change. If we have a very little bit, we're going to get a small change. So for an example, if we do 1 mole of carbon combustion, right, we get 1 mole of CO2. And we use minus 393.5 kilojoules. If we have 2 moles of carbon, then we get twice as much. So it's proportional. Whole number proportionality. It's great. So we can predict how much energy we're going to do by doing a reaction if we know 1 mole, and then we can use that to find out, well, if I have 5 grams of carbon, how much energy is that going to burn? So this is what happens. This is why guys can make meth in their trailer, basically, is because they figure out the amounts, they put them together, and then they get dirty glassware and the whole thing blows up. That's okay. Good riddance to good garbage. So delta H changes sign when reaction is reversed. Okay, so if we're going one way, it's positive, but if we go back the other way, it's negative. So we can use that to our advantage. If we're trying to go from one place to the other, but the equations don't match, you just turn them around and go the other way. And then change the energy sign. So we can keep track of the energy no matter what direction we're going. If we have the reaction in one direction, it costs the same amount of energy to go the other. Again, state functions. They're awesome. And they're real, turns out. I mean, as real as it gets for mankind. Recall that delta H, like delta E, is a state function. So Hess's law says delta H is constant whether a reaction takes place directly or in a sequence of steps. Yeah, Adrian.
Sorry about that.
No
you
worries.
go back.
Yeah.
I kind of got lost when you were
Okay.
explaining right now. You were saying, I don't know if you were talking about like the math, like law where you multiply 2 negatives and you make a positive. Is that the same thing?
No.
Or is it different?
No, that's a math law. This is more, if I go in this direction, it's minus 393. So if I take carbon plus oxygen and I do the reaction, I release this amount of energy.
Mm-hmm.
If I go from CO2 and I put in 393.5 kilojoules, I can make oxygen and carbon.
Yeah.
But it's a different sign because I'm going the opposite direction. So it's not like a mutability law or commutative law. It's the same energy going one way as it is the other.
Oh, okay.
Yeah.
Got it.
Is that tied up a
Yeah,
little bit?
yeah, it does.
Okay. So, for example, if I go from carbon to oxygen, I use minus 393, but if I go the other way from products to reactants, I have to put in that much energy. It costs me that much energy. So I can use these equations in either way, and I can use multiples of these equations as well. Because what I want to do is take known amounts that we know that we've measured already of delta H and apply it to a system of reactions to find out what the energy is for one smaller reaction. So delta H is constant whether a reaction takes place directly or in a sequence of steps. If a reaction can be expressed as a sum of several other reactions, then delta H for the overall reaction is the sum of the delta H's for these reaction steps. So what we can do is, what I usually do, and this makes it look a lot harder than it is, but basically, if I have AB plus C, so I have two reactants and I make a product, and then I go from C to D from product, it's the same as going from A, B to D, right? So I can subtract out C and just go A, B to D by using that reaction, those changes in heat. So if I do that, delta H total equals delta H1 plus delta H2. Right? And then over here, same thing. I get AB goes to C, that's delta H1. Right? So the change in energy for A plus B to C is delta 1, and then 2A plus C equals D, so that's the second step, delta H2. Then D plus E equals F plus B is delta step 3. And then I can cancel out these steps and get 3A plus E equals F, which is the total of plus 1, plus 2, plus 3. All right, so let's keep moving. It'll make more sense when you actually see an example. I hope.
Yeah.
I mean, I hope.
That's it.
So calculate delta H for the following reaction. So the one we just looked at. C plus 1/2 O2 equals CO, so carbon monoxide. So what we have is we don't have that number. What we have is C plus O2 yields CO2, which gives us minus 393.5 kilojoules per mole. And then we have CO plus half O2 yields CO2, which equals minus 283 kilojoules per mole. So we have to use those two to get what we need. Right? So to get the desired reaction, we reverse 2.
Why?
So we can get what we need. That's why we always reverse the positions.
But why 2, not 1?
Because we're trying to get to CO. Right? So if we look at the top reaction, right, our product is CO. When we look at reaction 2, in the direction that it's given to us, CO is a reactant. We don't want CO as a reactant, we want CO as a product, so we're going to flip that reaction around to make sure that CO is now the product.
Okay.
And since we flip the direction, we have to flip the sign. Right? And that's what we're talking about. So if I go this way, it's minus 283, but I started with what I want for a product, so instead of going that way, I'm going to go this way, and I'm going to add 283 degrees. Or kilojoules, I'm sorry. So and when I do that, then the CO2s cancel out, right? Because there's a CO2 on the product side and a CO2 on the reactant side. So I end up with what I'm looking for, carbon plus half O2, because I have O2 is now switched sides as well, so I have to subtract an O2, half an O2, from the original O2, right? Because it's now on both sides and half's left over, so that's what I get, right? So I add the two equations. You guys see that?
I do not see that.
All right. So
Maybe I'm blind.
let's go by.
Sorry.
So here we have, what we're trying to do is the top reaction here.
I see
right.
what you need to get. I understand.
Okay, so I have these two to choose from.
Mm-hmm.
We're going to leave this one going this direction because it gives us the carbon starting material.
Okay.
But then we look at the product, there's no product in the second reaction on the product side. It's on the reactant side.
Mm-hmm.
But we can flip the products and reactants by changing the sign and going in the opposite direction. So instead of going CO plus half O2 yields CO2, we're going to go CO2 decomposed yields CO plus 1/2 O2. And now that's what we're gonna turn around. So when we do that, CO2 now, which was a product, is now the reactant. It decomposes into what was the reactant, or now becomes the product, and we've changed the sign.
Okay.
Okay, so now when we add these two equations together, we have one on this side, one on that side. So it's like it's now the same as it was on the other side. So it's a spectator. It's not involved. It's out.
Okay.
Then we have carbon. Carbon comes down. We have oxygen. Oxygen, there's 1 mole on this side, but only half a mole on that side. So we subtract the half a mole, and we're left with half a mole. So now we have C plus 1/2 O2, and then we have CO on this side, and so it just comes down. And there's nothing to cancel it out on the other side. So now we have the equation we were looking for because we turned number 2 around. And we add those two together, we get minus 110, and that's that.
Okay, I see that.
Okay.
I didn't realize you were adding them together.
Yeah, that's how we get to the bottom. So we're just adding the heat one, that's from this slide, right? We're adding them together. This is exactly kind of what we're doing there. Delta H1 plus delta H2 gives us the final reaction. So if we want to look at it as a graph, right, we had this and this, and then so we just subtract one from the other to get that. Right, because it doesn't matter the pathway, it's still going to be 393.5 grams, and right, that's this, but you can get there by going CO 1/2 O2 to CO2. We can subtract that. So here's another one. Calculate delta H for the following reaction. So now we're going to take carbon plus calcium oxide plus oxygen yields calcium carbonate. We have 2 measured enthalpies so far. CO2 yields C plus O2. And then we have calcium oxide plus CO2 yields COCO3. So fortunately for us, right, I think on the reactant side we have calcium oxide, and then on the product side we have calcium carbonate in this reaction. So this isn't the one we're going to turn around. The one above it, and you don't always have to turn them around, but in this case we're going to, right? We have O2 on the reactant side, here it's on the product side. We have carbon on the product side, and we need it on the reactant side. So that's the one we're gonna flip. To get the desired reaction, we add the reverse of 1. So we reverse 1, change the sign to exothermic, and then we have calcium plus oxygen plus CO plus CO2 yields calcium carbonate, which is the reaction we're looking for. And we add the 2 enthalpies, and we get minus 571.8 kilojoules. So it's just a straight addition of the component parts. What you're going to have to be able to recognize is how to get the reactants on one side and the product on the other. One of the other things we could do is multiply by a coefficient, right? So if you needed 2 of something, you could multiply the entire equation by 2 and double the amount of heat changed at constant pressure. So Hess's law is kind of fun. It's a little puzzle.
You have a really weird, fun.
Well, when you spend as much time as I do, you know, you have to create puzzles that you find interesting. And they're actually somebody else. It's like, I also used to do the New York Times crossword puzzle every day. You know, you don't get any prizes for that. Just a lot of weird looks.
Yeah.
So here's another one. Did you guys finish that one?
Let's
So it's not just the product that you have to get the same, it's the whole thing, that whole example, you have to flip everything around to try to.
Yeah,
Because the first one, you just wanted us to get the CO2, but this, you want the whole thing.
correct. Well, the first one I wanted the whole thing too.
But you didn't really say that, you said you just need this.
Well, right, you just need to flip it to get this part because the other part was already set up.
But it has to match the whole part.
Right, so the whole equation, that's what we're looking for, right? We're looking for this process, the entire energy change of the entire equation. And it has to match exactly. Sometimes, like the test question will be like 4 parts probably.
If you flipped the first one though, and it didn't end up being that, can you just go back and flip the other one? Or is it not that easy?
Well, sometimes it is.
Mhm.
You have to know which one to flip based on what you're looking for, right? The reason I could see this was a flip is because I wanted carbon on the reactant side and it's on the product side, right? So that's basically, I'm already going, what?
Mhm.
But sometimes you have 2 equations that one has 2C on the reactant side already, and then in which case you wouldn't flip either one, but you might have to use both of them to get to 1C. Like we did up here with the half oxygen in the previous example, right? We needed half an oxygen, so if we didn't get that from our flip, we would have had to do something else to make sure that the reactants match the products. Because that's what we're really looking for. We're looking for the energy associated with the entire reaction, not just 1 to 2 parts. So we have to figure out how to get the entire reaction from the enthalpies that have already been measured. Okay, here's another one. Loading you up, yeah, Nathan.
Is delta H always given to us?
Sometimes. Right, sometimes we're calculating the delta H. Well, like sometimes we're given the entire delta H of a reaction, and then 2 steps, and we have to figure out what the delta H of the 3rd step is.
Yeah, but like in the initial stuff.
Yeah, we're gonna have, like on the practice test question, the heats of formation are given within the table that's associated with the test and within the problem. So they'll be there, and if they're not, you can come up and ask, I guess. And I'll go, oh yeah.
Why is this one 3 long?
Right, because it can be involved, there's more than 1 step. To get to this reaction, we have to do several steps, because we don't have that direct measurement, right? A lot of reactions aren't completely measured, but we have their component parts measured, so we can therefore figure out what the energy change is gonna be and whether it's worth doing.
I do not like this.
That's
Noted.
Okay.
pretty heavy.
So you
Just
flip
putting
2.
it out there.
Do you get it, Mike?
Okay, let's see. Any other predictions? I have flipping 2.
I say flip 1.
Because 1 already has components you need to finish it where they should be.
Oh, you're not saying flip 2 equations, you're saying flip
No.
number 2.
Flip number 2.
I say
Okay.
flip number 1.
All right, so we have CO on this side, and I think we gotta start with CO somewhere, right? Okay, so let's see what we do. Any other guesses? Okay. To get the desired reaction, we need to add 1 and 3, and then half of the reverse of reaction 2. So you were semi-right.
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 What do you mean half? You only flip half of it?
No, you flip the whole thing, but you only take half of the energy.
So you can
More.
choose how much of it you're gonna take? You don't have to take all of it?
I was
There you
not
go.
expecting that.
You can take what you want and leave the rest.
Wow.
But you should never have taken the very best the night they drove Old Dixie down.
Oh my god, can you do this on the board?
It's a little confusing.
This one's really
Yeah,
confusing.
this one is
You
a
gotta
little-
walk
little bit
before you
more
can
in
run,
depth.
and I'm limping. Like, I didn't know.
Well, I'll consider the request. So,
Or you gotta explain it with the green.
all right, let's
by
go
showing.
again. I wish I had these, I could fix the slide, but I'll do that another time. No, I won't. I'll never fix the slide. Anyway, so if we start with delta H for the following reaction, we have carbon
Mhm.
plus half O2
Yes.
plus Cl2 gas yields CoCl2. So we look for something, I always like to look for the product first because I'm a synthetic kind of guy. So CoCl2, the first one has all that. Good. So I'm going to leave that one the way it is. I look at the other two, they don't have the product I want. But if I look over at number 3, I see that carbon is on the reactant side and I want carbon, and oxygen is on the reactant side and I want oxygen. Good. So now carbon and oxygen are taken care of. But I don't have any chlorine gas. So I look, wait, I don't have any chlorine gas anywhere.
Yeah.
Well, that's not good news.
See, I.
Oh, wait, I do. It's in number 1. Settle down.
Number 1 and number 3.
So 1 and 3 stay the
So
same.
1 and 3 stay the same.
Yeah.
So I got my chlorine, I got my carbon, I got my oxygen. So what don't I have?
Well, you need to do math to get the half O2.
Yeah, true, I've only taken partial of
Yeah.
Well, and I also have what? I have CO
Yeah.
in number 1, right?
Yeah, when you swap the third one.
So if I don't swap 1 or 3, okay.
Yeah, that's
You're
why
right,
the,
you're right.
the board is
You're right.
needed.
Oh, wait, though. I have the rolling board.
That's what.
Mr. Rolling Board.
Oh, that's good.
But I
Pointing
get,
at.
oh, yeah, because I got this up here so I can look.
Yeah.
Because I'm not going to remember any of this.
Me either.
You don't have to say that, we already know.
Oh, sorry. Okay.
We already know, Billy. That's awesome. Okay, and at least it's fun today for me, because that's the, really I've been missing the fun for me part of this class. CL2, and today it is, and I don't know why, but I like it. CO, CL2. Oh yeah, it's because I'm already on vacation in my mind.
No.
All right. This could be the problem that makes me walk out the door forever.
Do it,
And
do
leave you with somebody else to come down here and finish this.
Oh, is that?
And then look at what you guys have done and go, oh my God.
Don't threaten me with
You
the
let them
big
do
gun.
that.
Get another professor?
Wouldn't that be great?
No.
Yeah, get Danae down.
That would not be.
Uh-oh, we might have to do some work. Okay, so COCl2. Oh, I love you guys, or I wouldn't joke with you. Really, I joke with you. I don't give a crap. Delta H. Do you know I got a PhD and this is what I'm doing?
Yes.
Isn't that amazing?
Is this retirement?
I mean, it must not have been worth anything, huh? Okay, so minus 110.4.
You're by the beach.
Oh my God, I'm gonna die.
I think I could make
Dying
more
of
money
shit.
working at McDonald's.
Yeah.
Well, except for they just made
No.
the robots, and
Manager
so
at
all those
In-N-Out.
people are going to be gone. Oh yeah, man. No,
Manager
because
at
that'd just be
In-N-Out.
like working with kids.
They make like
There you go.
80, 90 grand a year.
Well, you can make that doing this,
Well,
and this
then
is a
stay
lot
with
easier than
us.
that.
Because this is less stress, so stay with
Yeah,
us.
there's zero stress with this. Well, I mean, you know. Okay, what were we talking about? Oh, yeah,
number
yeah.
2.
So we have number 1, right?
Yeah.
Let's look at what this does with this reaction. I have CO here. Nowhere there. I have Cl2. Well, that's here, right?
Yeah.
And then I have COCl2, right? So that's here. So I've got a lot of what I need. I have what I need here. This is not necessary, but it's here,
Yeah.
right? So we'll keep that in mind. Now let's look at number 3. And that's carbon solid plus
Oxygen.
oxygen gas yields CO2.
Carbon
Alright.
gas.
Yeah. No,
No, it isn't.
no, it's carbon solid. We're looking at number 3.
Oh, 3, sorry.
Yeah, 3.
He's not out of order. Yeah.
You're out of order.
No, you're just not, you're not in that same order.
No, it's from a movie.
Oh,
Order in the court.
You guys,
I haven't seen it.
have you,
All I do is
Judge
chemistry.
Judy?
some good men, a few good men? Oh, you should see that.
We'll watch Michael
Well,
and
it's,
Vinny.
and especially if you,
When I have extra time on my
Tom
hands,
Cruise.
I'll
With Tom Cruise.
watch that.
you can't handle the truth.
You can't.
Okay, I can
Me
handle
nodding-
this class.
nodding in
Keep going.
agreement.
Keep going.
I don't know. Okay, so
3 is.
1 and 3. So 3 has carbon in the reactant side, oxygen on the reactant side, and then CO2, which we don't care about. So right now, let's circle those. Carbon, carbon monoxide and carbon dioxide we don't have. Right, you guys with me on that?
Yeah.
Right there. So let's look at reaction number 2. Whoa, squeaking the, I can't believe I can do that. That's not even possible.
2 carbon monoxide plus
Gas
CO2.
plus O2 gas, 2
2
CO2 gas. There we go, you can't read that at all. And then, and this is why they train these people to do this, equals minus 393, and I forgot to put the other one, 0.5. And we'll do that, because that's the way I'm feeling today. Kilojoules per mole. And you think I'm all over the place. You should see.
No, you gave the wrong
It's
one.
minus
Because we put 3 in the middle,
566.
but
See,
you
this
put
is why you need an
on.
assistant.
So
No,
number
I'm-
2, your bottom one is negative 566.0.
I don't take instruction well.
Okay.
Delta H. I'm used to giving instructions, not taking them. 566.0 kilojoules. And I don't do well with authority. Times, especially self-promoted authority. 393.5 kilojoules. Like, I'd have a hard time with poo.
Okay,
You
honey,
have the energy
you have the
switch.
energy switched. on the-
Again?
Yes.
That's what we're attempting to,
Yeah.
because you put 3 in the middle instead of on the end.
Okay. See, that's why you go in order. Just saying.
Oh my God.
Just saying.
This is so pathetic. I can't even believe it. Should I do it again?
No.
No, because we will walk out today.
Will you? You promise?
Yes.
What if I gave a class and nobody showed up? How much would I get paid then? All right, so probably more.
It's hourly, right?
It is hourly.
So to stay here.
Okay, focus.
Why would I stay?
Focus.
All right. Why?
Because I really want to learn this.
There you go. You heard it here first.
I don't know.
All right, so we have. Yeah, but I do.
I know, so explain
So do you
it to
think
me.
you'd be nice to me?
I'm being
Well,
very
one would
nice.
think.
I'm just trying
I
to
mean,
get you
Motivated?
back on
How
track.
fast does it have to go? I already went through this slide once in lab, lecture, whatever.
Okay.
All right, so we have CS plus half O2, Cl2.
Okay.
From equation 1, we had Cl2 here. We have CoCl2 in the product side. Reaction 3 gave us the other 2 reactants. Equation 3 doesn't have anything we want in the right order, right? As CO on this side, we have CO on this side. We don't have CO in the final equation. We have CO2 on this side, but we already have CO2 on that side. We don't want that, right? So we're going to turn this one around to cancel out these 2. So if we turn that around, now we have 2 CO2 gas yields or decomposes into 2 CO gas plus O2 gas, which you can't read any of that. But it's now what? Delta H plus 566.0 kilojoules per mole.
Okay.
All right.
Why did you flip it around?
So, because I have these 2 things that are in these 2 compounds, one is a reactant, one is a product. When I look at this reaction, I have the same product on this side. So if I were to add these in this direction that they're in right now, I'd end up with 3 CO2s here, but there are no CO2s there.
Okay.
I'd end up with 3 COs here, but there are none here. So I want to get rid of the part that isn't part of the reaction. So I have CO2 on the product side and CO on the reactant side. And in order to get rid of that, I have to flip this equation. So now CO2 is on the reactant side and on the product side when I add these equations. And CO is on the product side and the reactant side. So they'll cancel out. Only the problem I have with this now is how many CO2s do I have? 2. And I only have, I only need 1. So I could multiply this one by 2, but then I'd have 2 here. I would have to multiply everything by 2 up here, which you can do as well. But then you have to divide by 2 at the end because you don't need 2, you only need 1. So in order to cancel out the carbon monoxides, I'm going to divide this whole thing by 2. And then I get CO2 gas breaks down or decomposes into CO gas plus
Half oxygen,
half O2, yes.
gas.
And that's a gas. Boy, taking some liberties with our alphabet. And what do we do? Oh, and then so we divide this by 2, 566.0 kilojoules per mole. It's almost like I've been drinking, but I don't drink, so unless somebody spiked my coffee. Those darn baristas. All right, so that's that. And now what do I have? Now I have to add these all together, and I end up with this, because I have half O2 on this side and a full O2 here, so that leaves us with a half. These COs and Cl2 cancel because they're on the right side now, so these cancel, and this cancels, and now I'm left with exactly that equation, and you just add up the delta H's. All right, so we did that, and I had some fun to boot, and found out more than you wanted to know. All right, and so when we do that overall, we do the minus 110.4 plus minus 393.5, and plus minus 1/2. Why minus 1/2? What happened there? Oh, minus a minus, that's why. Because
So,
products minus
They're giving
reactants.
us an equation and you wanna find delta H.
Why do I have 2 minuses?
We don't have it. They gave us 3 equations with delta H. So with the possible numbers that they're giving you, the 3 possible options, you use those to figure out delta H from the top equation. So that's why we're manipulating those 3 so that we can change it around so it equals the top equation. That way when you manipulate the equations, you manipulate the delta H's. And so that's how you find delta H for the top equation.
Right, you sum up the steps of the equation that lead to the product. Yeah. So, yeah. Good. All right. The general strategy is identify the reactants and the products in the desired reaction and align the reaction steps accordingly. If necessary, multiply each reaction to achieve the proper stoichiometric coefficient, which would be like times 2 times 3. If reactants and products appear after summation, which aren't part of the desired overall reaction, add other reaction steps so that these are canceled. That's what we did up here, right? Because when we're adding these together to get this equation up the top, the balanced chemical equation we're looking for, and the change of heat that we're looking for going from reactants to products, we had options to get there. Sometimes you have to determine what those options are, right? And it's usually at this level, that's de rigueur. But doesn't have to. So, let's step, enthalpies of formation. So consider general reaction. So now we looked at what happens, we already looked at what happens with the reaction. Right, now we look at what happens with formation of elements. We're gonna skip over this. To devise delta H reaction pathway from the constituent elements. So if we can go back to the beginning and take everything into its elemental state and then go to the product state, then we can keep track of all the energy, and heats of formation are how we do that. The standard heat of formation, delta, in the 0, remember that means at standard temperature pressure. Delta H for the formation of 1 mole of compound from its constituent elements in their standard states. The corollary, delta H0F for elements in their standard states is 0. So if we have an element, it costs us no energy to form that element. We have to be aware of what elements are and what elemental state is. We have 7 diatomic elements that occur on the periodic table: hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. And those show up as 0s. So we have to recognize that and not try to find a heat of formation or freak out when you don't have one, because it's 0. So we have this is from an appendix of the book years ago. Calcium solid, that's elemental form, so it's 0. To form calcium oxide, which is calcium 2 plus oxygen 2 minus, in a compound releases 634.9 kilojoules, which means energy is released, it's exothermic. To form calcium carbonate, same thing, almost double. If we look at carbon in the graphite, which is elemental state, there's no energy cost to do that. In the diamond state, which is very small amount of energy, but it's still measured, even though it's kind of an elemental state. But it's formed by compression, so it's not really our traditional. It's not it. You don't have carbon formed at standard temperature and pressure. So CO gas minus 110. Is there anything positive? Yeah. It costs energy to form C2H4. Right? It costs energy to form C2H2, which is acetylene, which is used in some types of, it's a gas used in welding. C2H4, also ethylene, I said ethylene, and then C2H6 we're back to forming negatives.
The release of the energy, is it always set into combustion?
Okay, so in this case, that's not combustion.
Okay.
That's what it costs to put the elements together from their elemental state. So to make calcium oxide, when you put calcium and oxygen together, it releases 634 kilojoules of energy. When it's an element, it doesn't. So I don't know where you're going with that. Yeah, it's not the reaction; it's the energy to form that molecule or to do that interaction. Is energy released by putting those together, or does it take energy to put them together? So basically, the reason C2H4 is positive and C2H2 are positive is because it costs energy to make additional bonds between elements. So again, just notice that elemental states like oxygen are 0, nitrogen are 0, and so you can look up these heats of formation. You're not expected to memorize those. You are expected to realize if you don't see a heat of formation because it's N2, that it's 0. So when we go to find out the overall cost of reaction, okay. So using Hess's law, which says it doesn't matter how many steps we take, the total number of steps is the same as going from A to B. So whether we go A to B, B to C, D to C to D, and as long as we're going in steps and we get from A to E, then we're going to have the same energy. We can also do it by going from one thing and then decomposing it to the elemental form. So I guess I said that incorrectly. When you take something, when you form something and go backwards, it's gonna release energy. I said that incorrectly. So we have these different methods of looking at things. We can go a negative heat of formation by going the other way. So instead of forming and releasing energy, we break it apart and have to put energy in, and then we can form to make the products, we can release energy. So their change is always going to be final minus initial. So products minus reactants. That's how we find the change in heat. So what does it look like? That's what you care about. What is delta HF for the following reaction? So the heat of formation for the following reaction. So we're just doing the same thing with a different name, right? You're going to use the heat of formation, and they're going to look them up from a chart. So again, we have a chart. Anything you need is going to be provided. You don't have to guess what these are except for the element, right? So heat of formation, we're going to take the sum of the heats of formation of the products. So the sum of, 2 times HNO3. The heat of formation of HNO3 is minus 252.2. So we're going to do that twice because there's 2 moles. Let's see how this goes. So delta heat 0 of reaction is going to be the sum of the heats of formation minus the sum of the products minus the sum of the heats of formation of the reactants. So 2 times minus 252.2, and look at me leaving off units, minus 0 plus 7/2 0 So 0 because oxygen heat of formation is 0. And then minus 285, which is what? Water, okay? And that's gonna equal minus 219 kilojoules. I can't believe I left out the units. So why aren't our oceans boiling nitric acid? This reaction would release heat if it happened, but other factors, entropy. Stay tuned for the next class, which will be the second semester. And who knows if they're going to talk about it now. From occurring. All right, so this is university class slides. What is delta reaction, H reaction for the following reaction? So here's another one. So did we see that? Did that make sense? We took the heat of formation of the product, which was nitric acid, which releases energy, and that's why it's a question. Why isn't the energy boiling? Because it releases energy. Seems like that'd be a good thing. So heat of formation for the products minus the heat of formation of the reactants. The product is nitric acid. The reactants are oxygen, nitrogen gas, and water. Well, nitrogen gas is 0 because it's an element. Oxygen is 0 because it's an element. So that means only the formation of water counts, and so we subtract that. Do we see that? Moving on. What is the heat of reaction for the following reaction? The change of enthalpy of the following reaction. And why do we have enthalpy? Because guys like to create things for standardized pressure. So 8 aluminum solid, which is going to be 0, plus 3 iron Fe2O3, right, at minus 824 kilojoules per mole, and we have 3 moles. And then the reactant, the products are 4 aluminum oxide and 9 iron. So again, the difference here is the heats of formation that we're looking at for elements are 0, so they don't really count. So we have 4 aluminum oxides minus 3 iron oxides. And that gives us minus 4206. So again, this process of turning aluminum into iron gains us energy. And this is a fun one that we sometimes demo. Don't know if we can do it this year. So the transfer of oxygen from rust to aluminum powder gives off a lot of heat. This is called the thermite reaction. It's really fun, burns a hole in a bucket. Like I said, I don't know if we're gonna do it. Danae usually does it. Okay, so here's another one. Ethanol and gasoline, assumed to be all octane, so even though there are other hydrocarbons in there. Both are used as fuel. If gas is selling for $3.49 a gallon, what would be the price of ethanol in order for it to provide the same amount of heat per dollar? Densities and HFs are 0.725 grams per milliliter and minus 249.9 kilojoules per mole and 0.7894 grams per milliliter and minus 277.0 kilojoules per mole for octane and ethanol respectively. So this is the kind of problem that we use to check to see if you can synthesize the information. Step 1, balance the combustion equation. So we have to figure out what both combustions are, which means we have to know what ethanol and octane are, and I would give you those formulas because I don't expect you to know the organic names. C8H18, which is gasoline plus oxygen, I would expect you to know that that's combustion. So C8H18 plus 25 over 2 oxygens, that's the balance. We've had to balance this one before, 8 CO2 plus 9 H2O, and that way we are cumulative. Because if you've seen it before, you might see it again. And then for ethanol, it's C2H5OH plus 3O2 yields 2 CO2 plus 3 H2O. And remember, whenever we do combustion with hydrocarbons, which is carbon and hydrogen containing compounds, we are going to get CO2 and water. That's what makes it a combustion reaction. And that's why everyone's so worried about creating CO2, but not worried enough to plant trees. Okay, so calculate, but they will click alike. Calculate delta H of reaction for combustion. So what is combustion? We're going to delta H, we're going to take the products minus the reactants. The sum of the products minus the sum of the reactants. So they're given right here. Let's look at them. So we have 8 CO2s, we come up here, we find, there's the CO2. So we multiply that by 8. We add the other product, which is water. We look up here, and water is, oh, it's right here. Minus 241.8 kilojoules per mole. So we're good there. And then we do minus 249. And for what? Why? Oh, because oxygen doesn't exist, but octane has 249 because it's right here. So all we're doing is grabbing the heats of formation, and then, so this is just a plug and chug addition subtraction problem with multiplied by the coefficients. If we look at ethanol, same thing. So we're going to subtract the heats of formation for 2 CO2 moles plus the heats of formation for 3 water molecules, and then we're going to subtract ethanol and ethanol because there's no heat of formation of oxygen. So what does that look like? That looks like the heat of reaction is 2 times 393.5. This whole slideshow I left off. Wow, that's bad. 393.5 kilojoules plus 3 times 241.8 kilojoules minus the minus 277 kilojoules per mole, which leaves us with a grand total of minus. So they're both exothermic, but we're not done yet. So 5,700 kilojoules per mole. 1 mole of octane is this number of grams of octane. The density of octane is in grams per liter. Yeah, this is good. We're synthesizing all the things we've done. Well, it's about time. Gallons of ethanol, 46.1 grams per mole for equal heat. 1235 kilojoules per mole times 1 mole of ethanol, 46 grams of ethanol. So we're comparing cost. We're just shopping. We're just shopping here. This should be fun. Let's go shopping. That's what I say when I go shopping. Let's shop for some prices, comparisons on grams per milliliter. So again, you can follow, is this, oh, this isn't in your notes, is it?
We have provided it,
Okay, or take a picture of it.
yeah.
How did you get any of those numbers? Where are you finding them, and how did you plug it in like that?
All right, so we have kilojoules per mole. You saw that from our delta H heat of formation calculation? Yeah? Yes?
Yes.
Okay.
But they were negative, and now you've got them positive.
Yeah, that's wrong.
Okay.
It should have a minus number.
Okay.
Double click. No, that's
No,
a
it's
picture.
because I did it in another, oh,
Yeah, it's a picture, it's not a,
is it a picture?
yeah, you can't edit that.
Okay, so we'll just draw it on ours.
Yeah, that's just pretend there.
But that's a good observation. I can't believe I didn't do that. So anyway, I got 114.2 grams per mole by calculating C8H. Right? I calculated the molar mass of octane.
Okay.
And that's how I got that. And then I'm gonna do the same thing for methanol. I gave the density in the problem, right here. 0.7025 grams per milliliter.
Okay.
Okay. So that's where those numbers came from here. So this is a problem we just do, right? Grams per mole. So we're just using the conversion of kilojoules per mole to moles per gram to grams per milliliter.
I think it's just throwing me off because it says grams octane. Like, I would prefer to see it as the C8, you know.
Right.
I'm just
As C8H18.
not trying to nitpick, but
No,
it
I
just
get you.
seems,
But here I called it octane.
yeah.
So
Okay.
I see what you're saying. I should put that in there. Stay consistent.
I don't know.
Yeah, I like it. I can handle criticism. See,
You're not. In
I am not a crook.
You're not in the video. That's
Good. I wasn't trying to be. Anyway, So that's where we are with that. That's the last slide. Yay! So you can have the last 7 minutes to work on your
Okay.
crying, or I mean, nice clothes.